Hello everyone, I welcome you all in the C programming and data structures lecture. This is part 1 of Stack's linked list implementation. In this presentation, we will see how to represent a stack using a linked list. Okay, so without any further delay, let's get started. Here is the outline of this presentation. First, we will see why linked list representation. Why linked list is required. We are already aware about that we can represent a stack using an array. Then why do we need a linked list representation? Why should we prefer the beginning of the linked list as the top of the stack? This is one thing we should learn, that why we must prefer the beginning of the linked list as the top of the stack. This is what we will learn in this presentation. And finally, we will see the basic idea on how to write a program for linked list implementation of stack. Okay, let's first see why linked list representation. Why do we need a linked list to represent a stack? Simple answer is use linked list when the size of the stack is not known in advance. This is the simplest answer possible. We must use linked list when the size of the stack is not known in advance. Here is how we can represent a stack in an array. This is the array representation of the stack, right? Here you can see the size is known in advance. We have to put the maximum size of the array. That is why size is known in advance. But in case of linked list, there is no limitation on the number of nodes we can create. We can create as many nodes as possible. Okay, this is up to us. The user is capable of adding more elements to the stack, because the elements will always get stored in the heap memory, the dynamic memory, right? So there is no limitation on the number of nodes we can create. That is why we must use linked list when the size of the stack is not known in advance. Okay, so we got the idea why linked list representation is needed. Now we will see why should we prefer the beginning of the linked list as the top of the stack. Okay, now there is a debate behind this, why we should prefer the beginning of the linked list as the top of the stack. Let's select the beginning of the linked list as the top of the stack, and let's try to build the argument that why we need to select the beginning of the linked list, that is the first node of the linked list, as the top of the stack. Okay, this is how a stack looks like. Let us suppose that this is the initial state of the stack. There are 3 elements in the stack, right? This is the linked list representation of stack, and top pointer is currently pointing to the first node of this list. Obviously, here we are selecting the first node as the top of the stack. That is why the top pointer must point to the first node of the linked list, right? For push operation, a node will be inserted at the beginning of the linked list, because we have selected the beginning of the linked list or the first node of the linked list as the top of the stack. Let's say we want to insert element 50 onto stack. Let's say we are interested in pushing this element onto stack. This new element will be pushed in front of the linked list, right? We can push this element in front of the linked list. Obviously, we must put this element inside a node, and we must push that node, or we must insert that node in front of the linked list. And this is how it looks like. This is how our stack looks like after inserting this element. And top pointer must point to the first node of this linked list. So this is our new top. After this, for pop operation, every time the first node of the linked list will be deleted, right? This automatically holds because the top pointer is pointing to the first node of the linked list. Let's try to delete the first node of the linked list. Let's delete this node. This time, obviously, after deleting this node, top pointer must point to this node, right? Okay. But why we prefer adding and removing the first node of the linked list? Now we will see why we prefer this. Time complexity of adding a node at the beginning is order of 1, and time complexity of removing the first node is also order of 1. These two are constant operations. You can see that is why they are faster. But what if we take the end of the linked list as the top of the stack? What happens if we take the end of the linked list, that is the last node of the linked list, as the top of the stack? Will the operation of adding a node at the end and removing the last node takes order of 1 time? Let's see this. Let us suppose this is the initial state of the stack, and currently we have this element inside the stack. The head pointer is pointing to this node, and top pointer is also pointing to this node. Okay. Now we want to add a new node at the end, and we'll make this pointer point to that node, right? After adding, this is how it looks like. And let's say we add one more node to this linked list. Then this is the final state of the stack. You can see the top pointer is pointing to the last node of this list, right? Obviously, the time complexity of adding a node at the end takes order of 1 time. This is a simple operation because there is always a pointer pointing to the last node, and hence we can easily add a new node at the end of the linked list. But what about removing the last node of the linked list? It is not difficult to see this, that time complexity of removing the last node is order of n. But why is that so? How will make this pointer point to this node? We don't have the address of this node, right? For this we need traversal. In order to get the address of this node and in order to make the link part of this node null, we need the address of this node. For this, traversal is required. Let's say we will create a temporary pointer, temp, and we will use this pointer for the purpose of traversal. Here we have to move this pointer towards right. And then after this, we can see this, that currently this is pointing to the second last node of the list. Now we can easily delete this node and make this pointer point to this node, and obviously we can update the link part of this node as well. Deleting the last node of the singly linked list requires traversal, isn't that so? If we want to delete the last node of the singly linked list, then it will take order of n time because it requires traversal. We have to traverse the list in order to remove the last node of the linked list. That's why order of n is the time complexity of removing the last node. I hope you got the idea why we are not preferring adding and removing the last node of the linked list. Let's see the time complexity comparison. Inserting a new node at the beginning takes constant time, and deleting a node at the beginning also takes constant time, right? But what about inserting a new node at the end? It takes constant time. And what about deleting a node at the end? It takes order of n time. That's why we are not preferring adding and removing the node at the end of the linked list. We must prefer adding a new node at the beginning and removing the first node of the linked list. Okay, you can see these are faster operations. Now we have got the idea why should we prefer the beginning of the linked list as the top of the stack. Now let's see the basic idea on how to write a program for linked list implementation of stack. The code of the push function must be similar to the code of inserting the node at the beginning of the singly linked list. And similarly, the code of the pop function must be similar to the code of deleting the first node of the singly linked list. I hope this is clear, right? We are already aware about this. If we want to push an element onto a stack, and if we are representing a stack as a linked list, we must write the code of the push function as like inserting the node at the beginning of the singly linked list. And for the pop function, we have to write the code for deleting the first node of the singly linked list, right? So push and pop functions are simple to write. After this, if we are interested in checking the Stack Overflow condition, then we can check this through malloc function. How? Stack Overflow occurs when there is no space left to dynamically allocate the memory. Although Stack Overflow is very rare, but when there is no space left to dynamically allocate the memory, then Stack Overflow can occur, right? In that case, malloc function will return null, okay? If at all it is the case that malloc returns null, then it means Stack Overflow. Similarly, Stack Underflow occurs when the top is equal to null. Okay, when top becomes null, then Stack Underflow occurs in that case. Top is the pointer which always points to the first node of the list. If it is the case that stack is empty, then it means that the top must be null. Top must not point to any node. These are all the basics we must remember. Now, this part is also clear. I hope all these three things are clear to you. Okay friends, this is it for now. Thank you for watching this presentation.